Okay, so far we have covered the Metropolis algorithm, okay? Okay, and the purpose of the Metropolis algorithm is to generate a sample of values from a target distribution, right? Okay. Why would we use the, well, maybe before we even get into the why, what's the difference between using, say, the Metropolis algorithm versus inverse CDF or rejection sampling? What's going to be the primary difference there? Because they both generate a sample of values from a target PDF. So how does the Metropolis algorithm differ from the other methods of generating random values? They're not independent, okay? So the values generated by the Metropolis algorithm are not independent, whereas values generated by inverse CDF or rejection sampling, those values will be independent, or convolutions or transformations, those are generally going to be independent, okay? So values from the Metropolis algorithm and other Markov chain Monte Carlo methods will not be independent, okay? Contrast to inverse CDF and rejection sampling, convolutions, those produce independent values. Okay, let's just talk about the steps in the Metropolis algorithm. Okay, so here the steps are, we'll say at time k, our value is x super k, all right? And we will say we have target PDF P, and we have proposal, have a proposal distribution. And I think the last time I used the letter G or something, I'm sorry to change it up, but we're going to just call it Q, okay? Sorry for the change of letter. We have a proposal distribution Q, and we will propose a value x star generated from Q of x star given our current value k. So Q is uses our current value xk to kind of determine its parameters. and then our proposal value x star comes from this proposal distribution. Okay, so we propose a value, and then we calculate the probability of move. Of moving to the proposed value. So we'll say p move is going to be equal to the minimum value between p of x star versus p of xk. Okay. So the consequences of this is if the proposed value x star is, has a higher probability than your current location, you will definitely move there. And then if it has a lower probability, then x at time k, then you might move there. You might move there, and that happens with probability of p of x star divided by p of xk. So divided by the proposed divided by the current. All right, and then that's it. And then if you do move, the next value is x star, and if you do not move, you still generate a new value. Another value, or you still generate a value for the sample. It's just the same value you currently have. Which is xk. All right, is this okay? And we, I coded up the example on Friday for the island hopping thing. We said, if the island, if our target distribution, is proportional to the populations of the islands, which is, proportional to their island numbers, then this is going to be our target distribution, and we coded a function for that, and then we coded a function for a proposal function to, you given your current value, it will propose a new value, and then and we use the Metropolis algorithm to generate a bunch of values. Is that okay? All right. Let's talk about why one would want to use the Metropolis algorithm. Like why? Why would we use the Metropolis algorithm? Okay. I'd say the biggest advantage is that the target distribution you don't actually need to know the exact form of the target distribution. You only need to know that it is proportional to something, okay? So a big advantage is that the exact form of the target PDF does not need to be known. Okay? You only need a function that is proportional to the target PDF. Okay, so how can this help us in Bayesian statistics? So I will say this is helpful for Bayesian statistics. All right, can anyone think of why? So in Bayesian statistics, what is it that we're trying to estimate, or we're trying to get? Posterior. We want the posterior distribution, right? So in Bayesian statistics, we say the parameters that are not known to us, these are not single fixed values, but they're defined by a posterior distribution. And in the homework that you guys just turned in, I hope you saw that the very last problem, the purpose of that was to show how Monte Carlo methods and Bayesian statistics work together, right? Because that integral that you would have had to calculate, I think it was like, what's the probability of getting, I don't know, at least whatever, something, right? There's some kind of question, and in order to solve that, you would have had to integrate that function h of x multiplied by the PDF of the thing, which was a beta distribution. And I don't know if anybody wanted to even try to do that analytically, okay? Because having that beta distribution in there, along with the target function, the h of x, that would have been a messy integral, okay? But I think in the homework it was probably computationally one of the easier problems to do. All you had to do was generate random values from the beta distribution, and you apply h of x to it, and then you have a pretty good estimate of the answer, okay? You avoided the hard math. So I'm hoping that was like, oh, here's a use for this, okay? Furthermore, when we talk about the Metropolis algorithm, this is going to be helpful for Bayesian statistics for another reason, okay? So in Bayesian statistics, we want that posterior distribution, and in the last homework assignment you guys completed, we saw that if you have the beta binomial model, the posterior distribution ends up being a beta distribution itself, right? And that works out nicely, okay? And there was one thing we avoided, and that was trying to figure out the normalizing constant. I think in the work, we just said, when you multiply the binomial likelihood by the beta distribution prior, it looks like it's going to be in the form of the beta distribution, and therefore the beta distribution normalizing constants just got to work out, okay? Because we know all beta distributions will integrate to 1, okay? There will be other situations where it's not as pretty, okay? And so over here, so I'm going to just write, in Bayesian statistics, we want the posterior distribution, okay? And the posterior distribution is the probability of our parameters theta given our data, okay? And we say, so this is the probability of parameters theta given our data, okay? And this is equal to the likelihood of the data multiplied by the prior distribution multiplied by the prior divided by the marginal probability. Okay. And we said the marginal probability, as far as theta is concerned, is a constant, okay? Because the data is fixed. It's something we have already observed. There's no uncertainty about it. The data is fixed. So this marginal probability, this is a constant. Okay? And it's equivalent to the numerator, the sum of the numerator or the integral of the numerator across every single possible value of theta. Okay, this is a constant. It is equal to the sum or integral of basically the numerator across all possible values of theta. And its only purpose is so that when you integrate this entire thing, is that the entire integral will be 1, or the entire sum will be 1, okay? That's its only purpose. It's an important purpose. I don't want to marginalize its purpose here, but that's what it serves, okay? Its function is to ensure the PDF integrates to 1, or the, or the PMF sums to 1, which is very important, okay? But other than that, it's just some constant that's very difficult to find, right? And this is a constant, and in general, this constant is difficult to calculate. This constant is difficult to calculate. Okay, so this is why the Metropolis algorithm is useful, okay? Because in the Metropolis algorithm, this is going to be our target PDF, okay? Probability of theta given data, okay? And so in the Metropolis algorithm, okay, generating X star from Q is easy, right? Just pick a Q, pick a proposal distribution that's easy to work with. Don't pick some crazy proposal distribution. Just pick an easy distribution to work with. Generating your proposed value is easy, okay? Especially if you pick an easy distribution Q. Okay, and then I guess the hardest part is finding the probability of your proposed value divided by the probability of your current value, okay? Probability of proposed divided by probability of the current, okay? So the proposed value, if we say we've got, in this case, it's going to be theta star given data divided by probability of your current value, okay? And this will become, over here we've got probability of data given the proposed theta star times the theta star divided by probability of data. And then over here we would have probability of D given theta k times the probability of theta k divided by the probability of data, okay? So this is, because this is our target PDF, so using this is the probability of the proposed value divided by the probability of the current value. In this case, theta k and theta star. So that's what we have. And what do we notice? The theta d's, or I'm sorry, not the theta d's, the probability of D, the marginal probabilities, these cancel out. These cancel out. And so we only need to work with the numerator. And this will be proportional to, so this is our target PDF, right? Our target PDF is this, and we have the numerator which is proportional to it. We only need the numerator which is proportional to the target PDF, okay? And so this is incredibly handy. Okay. Furthermore, if the prior distribution is flat, okay, as in it's just a constant, like we're going to just say every single value of theta is equally likely, then what does your target PDF reduce to? If probability of theta ends up being, if this value ends up being a constant, then what happens? Then we can ignore that too, okay? And you only have to worry about the likelihood of the data given, you know, your current value. Now maybe you don't want to use a flat prior, and that's totally fine. You can use a prior distribution that's not flat. But this is a huge, you know, maybe you haven't done enough Bayesian statistics to appreciate how much of a headache this reduces, okay? Because trying to figure out this marginal probabilities to ensure that the PDF integrates to 1, that was a huge problem, okay? And so now we can avoid that problem and we can just say, hey, I've got the numerator part only, okay? And you can still get values now from the target distribution with the Metropolis algorithm, okay? So even though we only have the numerator, we can get values from the target PDF, which is impressive, okay? I think. Well, it is. So, okay. So with the Metropolis algorithm, we can generate values from the target PDF, even though we only know the numerator in Bayesian stats. Okay. So that's handy. The Metropolis algorithm can be extended and generalized further into something called the Metropolis Hastings algorithm. So one requirement of the Metropolis algorithm is that the proposal distribution Q is symmetric, okay? And what that means is that the probability of proposing some value x given your current value has to equal the probability of proposing your current value if you were located at that proposed value. Okay, so like if we're currently here and we're using like Q is normal, we might propose some value here, and the idea is that this probability the probability of proposing this value versus the probability of proposing this value, they're at the same height. Okay. All right, so that's what that height represents. Okay, we can relax this requirement if we relax the requirement so that Q does not have to be symmetric. Then we get something called the Metropolis Hastings algorithm. Okay, so in the Metropolis Hastings algorithm, Q does not need to be symmetric, and so these will be the steps in the Metropolis Hastings algorithm. All right. So we have xk at time k. We have target PDF P, and we have proposal distribution Q, which is not necessarily symmetric. Okay, and so the steps are propose x star from Q given your current value of x. Okay, and then the probability of moving to x star is going to be the minimum between 1 and, so you have the proposed value divided by the current value, but then you have to say you have to adjust the acceptance probabilities by taking the kind of the difference between proposal probabilities, okay? So this ratio adjusts for any difference in proposal rates. Okay. So if you're more likely to propose values going to the right versus going to the left, okay, in order to kind of balance that out, you say, you know, how much more likely are we to go to the right than we are to go to the left? Then let's kind of take that ratio and bring that into whether we decide to go that way. Okay, so you just kind of, you're correcting for the, you know, imbalance in the proposal distribution, right? Okay, and then, you know, from this point, then it's exactly the same, right? Sample U from uniform 0, 1. And then 4 will be if U is less than P move, then X star will be your next value. And if not, then reuse your current value, xk, as your next value. So each iteration produces additional values in your sample. It's just that if you didn't accept the proposed value, you'll just reuse the current one. All right, is this okay? Let's see. Maybe I can show you that this works. All right, so why does the Metropolis and Metropolis Hastings algorithm work? Or how? Maybe I should say how. Okay, like in that, how do we know the stationary distribution will be the target PDF? Okay, well, the stationary distribution happens when we achieve something called detailed balance, all right? Detailed balance, so, well, I guess detailed balance is a sufficient condition for the stationary distribution, okay? So we can achieve the stationary distribution when we have detailed balance. Okay, detailed balance is not a necessary condition, but it's sufficient in that, you know, it kind of goes above what's necessary. Okay, so we're going to say the transition probability is going to be written as T of x k plus 1 given xk, all right? And this is the probability of transitioning to the value xk plus 1 if you are currently at xk. And we have detailed balance okay, so this is basically the probability of transitioning from xk to xk plus 1 multiplied by the probability of being at xk, all right? And that's going to be the probability of transitioning from xk plus 1 to xk times the probability of being at xk plus 1, okay? So illustratively, if we have a, here, maybe I'll say this is k, and this is k plus 1, okay? It's basically when the amount flowing this way is equal to the amount flowing this way. Okay. So when those two are equal, then it's equal, right? Then you have the stationary distribution. If the amount flowing from this location to this location is equal to the amount flowing from this location to this location, then we've achieved detailed balance and we're at the stationary distribution. So I think in an earlier two-state case, we had A and we had B, and we said the transition probability of going from B to A, this was equal to, I don't know, 0.4? Or was it, I forget what I wrote, 0.3? It doesn't matter, all right. And then the transition probability, sorry, this is the transition probability of going to A, given that we're at B, is equal to 0.4, okay? And we achieved detailed balance when the probability of being at A was 4/7 and the probability of being at B was 3/7. Okay? And we saw that if we have 4/7 times 0.3, then you'll get like probability of A times the transition probability of going from B to A is going to be 4/7 times 0.3, I guess 1.2 over 7. And then if we have probability of B times the transition probability of A given B, this would be 3/7 times 0.4. This would also be 1.2 over 7. Okay? And so the amount flowing from A to B is equal to the amount flowing from B to A. Okay? And so we have detailed balance there, and we're at the stationary distribution. All right, so going back to the Metropolis Hastings algorithm, right, there are two possibilities for a proposed value x star, okay? One is we reject x star, okay? And in that case, the next value, xk plus 1, is going to be equal to xk. And then 2 is we accept the proposed value, and in that case, xk plus 1 is equal to x star, which is different from xk. Okay, so if we reject, all right, so we'll just look at the rejection kit scenario first. If we reject x star, okay, we have detailed balance. Because xk plus 1 is equal to xk, all right? That it's kind of trivial. I'll just show you. So the transition probability of going to xk plus 1 from xk multiplied by the probability of being at xk, just this becomes the transition probability of being at xk given xk times the probability of xk, right? Because xk plus 1 is xk, and then we just have to show that it equals that the transition probability of going to xk, given that we're at xk plus 1, this just becomes the transition probability of xk to xk multiplied by the probability of being xk, all right? So because xk, the next value is the current value, so of course that's going to be trivial here. All right. So, you know, the probability of going to itself, going from one state back to itself, is equal to the probability of going to the state back to itself, which is what we're saying here. All right. Oh man, I'm going to run out of time. Well, let me at least get started here, and then I guess we'll finish this. Okay, so what we need to show we still have detailed balance when we accept x star as xk plus 1. Okay, so when the next value we get is that, we have to show this. Okay, let's just keep in mind, so our transition probability when we accept, the transition probability is, okay, so the transition probability of going to xk plus 1, given that we're currently at xk, is going to be equal to the minimum of 1 and probability of xk plus 1 divided by the probability of our current value, xk. And then, you know, I'll go ahead and I'll do this for the Metropolis Hastings algorithm, it's all you have to do. You can just throw away all of the q's if you don't like it. In here is xk given xk plus 1 divided by q of xk plus 1 over xk multiplied by the probability of proposing that okay, so this is probability of moving times probability of proposing xk plus 1, okay? So that's going to be the transition probability. It's going to be the probability of moving there multiplied by the probability of proposing, okay? The value in the first place. Okay, we'll stop here. We'll finish this kind of derivation out, or I don't know, proof or whatever, and we'll see you guys on Wednesday. Okay.